Okay, well, thank you again to the organizers for being invited to speak here. It's a great honor. It's a fantastic meeting. In trying to, decide how to approach this, I thought, in a way, one of the great benefits of this whole Newton program has been bringing together machine learning people and statisticians. And certainly, as a machine learning person, I've learned enormous amounts from the talks from the statisticians. Now, I'm not hoping that you're going to learn anything like as much from what we have to say, but I thought it would be useful in a way to try and give a bit of background to the kind of things machine learning people have, or some machine learning people have been studying in relation to sparsity, some of the issues that have come up in that area, and throw them out to you, and maybe you can do something much more sophisticated. So I would say, if don't be fooled if it does seem rather simple and straightforward. That's because it is simple and straightforward. But I hope some of the ideas will also, spark interest and further research. So I should emphasize, though, it is a biased view of sparsity and machine learning, and there are many aspects, particularly the Bayesian approach to sparsity, that I'm not going to cover, and it's biased towards the things that I've been involved in, and so don't take this as a sort of overview of all of machine learning. Okay, so this is really saying what I've already said. Sparsity has emerged actually as one of the key techniques in machine learning to enable scaling to large data sets and to high-dimensional data. Some methods have been developed independently in statistics and machine learning, and others have arisen more in one or other community. And so, in a sense, a lot of it, sometimes, we're reinventing the wheel to some extent. But I think still, even when that happens, you get a new perspective, perhaps, on some old problems. So this is an overview of what I would like to cover. So I'm going to sort of start with a general discussion of approaches to sparsity. I'm then going to talk about sparsity compression bounds, which were quite an old topic in machine learning, computational learning theory, but were given a new spin, or not that new, but a newer spin in something called the set cover machine, which I'd like to also mention. Then I'll move on to the L1 sparsity that we've been hearing a lot about this morning and in general, and an algorithm inspired by that called linear programming boosting, and then talk about a lasso-style correlation analysis, so very closely related to Rob's talk, and then the algorithmic implementation of that, which also gives a new lasso implementation algorithm, which we can go head-to-head with Rob on his coordinate descent. I think actually it's quite closely related, but you'll see when I get to that stage. Then I'll talk a little bit about coming back in a way to the earlier compression bounds and reusing them in a sparse analysis of a sparse PCA algorithm and matching pursuit algorithms. So there's sort of a refrain coming back to the earlier discussion. So that's sort of an overview. So as I said, sparsity has played an important role in computational learning theory research, and the early bounds were on generalization. So sort of maybe the way that machine learning people have tended to think is more about not consistency, but just in terms of bounding performance on a test set. And this method uses a sort of sparse reconstruction in order to drive a bound of that type. I'll actually describe that in a moment. So I'll look at that and show how it's actually been translated into this set cover machine learning algorithm. Then I'll, delve into the L1 regularization, again with a generalization bound as motivation for this boosting algorithm, and then I'll return to this matching pursuit. Okay, so here's the sort of early idea from computational learning theory of a sparse compression bound, and I think it's generally been regarded as a folk theorem. So the idea is that if you have a training set S and you have a mapping which subselects a subsample of S in such a way that from that subsample you can reconstruct the output of your learning algorithm by some method, which might be, I mean, there's nothing about the computational efficiency in this at all. It's just an information theoretic condition. Then you can bound the performance of that algorithm, which in a way that the size of this compression set and its empirical error of this is the empirical error k, d is the size of the compression set, are essentially entering into this in roughly a linear way. So the sort of size of the compression set plus the number of errors divided by 1 over the sample size minus those values enter in as a bound on the generalization. So the idea is that if you can find a small subset which enables you to reconstruct your output function that your algorithm is returning, then you're in good shape as far as performance on a test set is concerned. So perhaps the simplest example is the support vector machine. If you think about a support vector machine, you know, you generate from your data this hyperplane, and it's supported by a small subset typically of support vectors. If you rerun the algorithm on the support vectors only, you get the same solution. So in a sense, you can reconstruct, think of this lambda of S as being the support vectors. You can reconstruct the support vector solution by essentially phi here is just rerun the algorithm in this case on that set of support vectors. So you can bound now the performance of a support vector machine with a roughly performance that is the ratio of the number of support vectors to the number of training samples overall. So it's a very kind of nice way of thinking of it. And it is a high confidence bound which holds with high probability. I've used the notation delta here, which is perhaps more standard in machine learning. So this is a bound that holds with probability 1 minus delta over the generation of the supposed IID training sample. So assuming an ambient distribution. So this was back in 1986 by an actually unpublished manuscript at Littleton and Barmouth, but was then published with some additional tweaks and ideas by Floyd and Barmouth in 1995. So the proof is actually very neat because it just relies on counting the ways you could choose those sets in order to generate the the compression set. So there's only a small number of ways if it's a small compression set that you could choose that set. And then if you imagine having made the decision about which that set should be, essentially the rest of the data is now can be viewed as an independent sample which can be used to verify the quality of the function determined by that choice. And so you don't even need the sort of double sample trick that one would normally consider using in say a VC bound. You can actually use the test examples from the sample effectively to get the quality of your chosen function. So this is actually it also produces for that reason relatively tight bounds. So even though this is not probably the right way to think about support vector bounding, the bounds produced by this approach are often tighter than the sort of margin-based bounds that actually motivate the actual optimization in a support vector machine. You can also include additional side information, and you pay obviously a cost in terms of the number of bits of extra information you need in order to perform that reconstruction. But certainly it inspires the optimization of sparsity in an algorithm. It's also spawned one of the sort of big unresolved questions in learning theory, from a machine learning view at least, which was this question of the relation between the VC dimension and the existence of a compression scheme. So if you note that roughly speaking, you can think of the VC dimension and the compression order as behaving very, very similarly. In terms of the bound on performance, certainly, you know, the sort of scale of the bound depends on the order of the compression scheme. That means the size of the compression set in this case, in exactly the same way as it would on the VC dimension. So the question arose, you know, is there a general result that says that given a VC class, can you find a compression scheme for that class? And this is true for maximal VC classes, ones where you include as many sets as you can, you know, constrained on the fact that you have a VC of a certain value, but it's open in general. So this is one of these questions you definitely don't want to look at because it's a killer and can burn time like there's no tomorrow. So what I wanted to mention, I mentioned this idea of a different application of this approach. In the proof of the theorem, if you look at it, you don't actually need to predefine the function class in the way that you would have it with, say, the VC class. You have a predefined set of, you know, set system that you know and are trying to identify through your compression set. Actually, you can use additional information from the chosen examples in your reconstruction. So you have a sort of data-dependent version of this reconstruction bound, which essentially goes through. And so this suggested this idea of the set cover machine. So the way this works is you actually use the data examples to generate a set of, if you like, weak learners. So the way in which the basic set cover worked was to consider pairs of examples in the feature space and define spheres by taking one of the examples as the center and the other as defining the radius of the sphere. And then you take a logical combination of those spheres. And the question, you can have a greedy algorithm that essentially tries to find that combination which will give a good classification on the training set. And the algorithm is guaranteed to find a good approximation if a small cover exists. So the idea is, you know, if there is a sort of simple way of classifying the data in terms of these spheres based on your training data, then the algorithm will find a reasonably good approximation, not optimal, but reasonably good. So this translates then into a sort of a reasonably, you know, good approximation algorithm with a guaranteed performance bound of the type that I described earlier. So it's quite a nice kind of combination of, if you like, optimizing sparsity in a way that if it exists, you'll find it, and furthermore, you'll get good performance. And indeed, the performance that you get on sort of, you know, simple data sets is quite comparable with, say, something like an SVM. If you take the hard margin SVM, it's probably, this is doing on the whole better. If you take the soft margin, doing slightly worse. This is the set cover machine here. But the bound, this is the test error, and this is the bound that you would expect on the test error, is not, you know, a million miles apart. So these bounds are sort of remarkably tight compared to other bounds that we've seen for, say, you know, the support vector machine. So, you know, I feel, you know, this is kind of an unusual approach to gaining sparsity or using sparsity. Other alternatives than this idea of spheres have been tried as well. I should say that probably on larger data sets and certainly high dimensional data, this technique doesn't appear to scale so well. So on these small UCI data sets, it seems to work very well, but our experiences with higher dimensional data is that it doesn't perform as well as, say, the support vector machine. Okay, so I'll move on now to my next topic, which I wanted to cover, which was this link with the L1 sparsity. So here I wanted to first mention the I think rather nice fact about Rademacher complexity. So Rademacher complexity is a measure of the complexity of a function class, which is taken as its ability to align or correlate with random noise in the sense of Rademacher variables here. So you take the supremum over the function class of this correlation. So more traditionally, there's an absolute value here, but one can actually use this as well, particularly if the class is closed under negation. So this is sort of perhaps simpler to see what's happening. So this is a kind of a measure of complexity that can be used to bound test performance. And you know, that I think probably well known in statistics as well, community. The nice property of the Rademacher complexity in connection with the L1 sparsity is the property that if you move to a convex hull of a set of functions, you don't actually increase the Rademacher complexity. So you're getting an added richness in your function class without actually paying any price in terms of this complexity measure, at least. So this seems a very nice property. I mean, there's a factor b in here because I'm imagining that the one norm is bounded by b. But in general, if the one norm is bounded by one of this convex combination, then this b will be equal to 1, and there'll be actually no increase in the Rademacher complexity. Basically, that's because if you take a simplex, it's always the corners of the simplex that achieve this maximum. So, you know, if you just take the convex hull, it doesn't actually increase. So it's not that surprising, but it's a nice property that actually can be, I think, used to motivate, well, this generalization bound, which is, again, just taking now convex combinations with one norm bounded by b, then you get this b times the Rademacher complexity of your, if you like, basic function class. Think of this in a boosting context. This h would be the weak learners, and you're trying to take linear combinations of weak learners. And this is the one norm of the linear combination. These are the slack variables that you might introduce in a support vector machine, which are just basically the amount by which you fail to meet a margin of 1. And so you get a nice bound that apparently only relies on the complexity of the weak learners, not on the complexity of the actual class you're using, which is the linear combinations thereof. And so this is sort of directly applicable to a boosting style algorithm, or in general what's sometimes referred to as the linear programming machine. Apologies for all these machines in machine learning, but they tend to like to coin phrases that sound mechanical. Probably not a good practice. Anyway, the Rademacher complexity in the case of taking n weak learners or n features, it does scale as sort of log n. So you're getting this nice scaling property if you add a lot of features in the bound. But it also suggests an optimization similar to that of SVMs, which basically is this. So you seek a linear function in your features such that it has a margin of 1, possibly with some slack variables indicating failures to meet that margin, and you minimize the one norm of the weight vector together with the sum of the slack variables. So it's sort of a very close to lasso, if you like, here. And if you write that out and move to the dual, so it's just a linear program. There's actually a boosting algorithm, which probably, Rob would call lasso boost probably at this point. But we didn't know about lasso boost, so we called it linear programming boosting. So it sort of sounds really clunky compared to lasso boost. But anyway, it would be, maybe lasso boost exists, so I don't know. But basically the idea here is that you, if you look at the form of this dual, it has a condition over the weak learners. So this is a condition that has to be satisfied for each of the weak learners. Okay, so the idea is that you can start with a small number of weak learners, just one initially, solve this dual problem with that single weak learner or small subset of weak learners, So it's a very sort of constrained, small problem. I mean, we're thinking of n being very large here. So, you know, a small subset of them makes this a much more manageable problem. And then you can simply check this inequality for the other guys. Okay, now if it turns out that that inequality is satisfied for all of the other guys, you're done, right? You've got the optimal solution, and you don't need to actually go any further. If, on the other hand, you find that some other weak learner actually fails to meet this bound, then you can draw it into your optimization, add it, and resolve with that extra column. So this is actually just what's known as column generation in linear programming theory. So the idea is that you're using the sparsity of your, and the point is you'll only actually need to include columns in the end that have non-zero coefficients. So this actually, you know, will correspond exactly to the sparsity of the solution driving the algorithm. So this is something a theme I wanted to build a little bit, was this idea that you can, you know, L1 sparsity is very nice because it can also make your algorithms efficient. I think this is very close to what Rob was saying in his coordinate descent. I mean, the fact that you actually only have to update a small number of the features makes the algorithm fast. So in this case, you end up with this algorithm known as column generation or linear programming boosting, and basically you always look for the maximizer of this, which is exactly the criterion you would normally use in boosting to introduce a new weak learner. If you find that the maximum already satisfies what the optimal beta that you've got from your previous round, then you finish, you're done, you just solve the primal with that set of weak learners and you're done. If, on the other hand, this J star is exceeds the value exceeds beta, then you add it to your set of weak learners and you solve the dual LP. So it's slightly different from a normal boosting algorithm because you're updating all of the weights. Okay, but notice that the distribution is also being updated in your algorithm. The distribution corresponds to these dual variables, the Lagrange multipliers, and they do satisfy that they sum to 1. So you actually, you know, this is exactly corresponding to, you know, updating your distribution as you would, say, in AdaBoost, but as an output of the linear program that you're solving. And so you've got a boosting algorithm that is directly optimizing a bound, which seems a nice thing to do. Of course, you know, there's a lot of controversy about whether, you know, the margin hypothesis explains what boosting is doing. I don't want to enter into that, but I mean, it's just nice to have a bound, okay, a margin bound, which drives an algorithm. You know, that doesn't necessarily say that that's exactly why the algorithm does what it does, but at least it's sort of putting a bound on its performance. Maybe it's doing better for some other reason, quite possibly. The other nice property of this is you do have a stopping condition. You know when to stop, which obviously with AdaBoost one typically, you know, doesn't. And it typically will, the performance, I haven't got results to show you, but the quality of the performance is very comparable to AdaBoost, sometimes slightly better, sometimes slightly worse, but the sparsity is typically much smaller. I mean, much fewer weak learners included. I mean, in AdaBoost you have this sort of typical thing run for a certain number, you know, 100, 200,000 iterations, but here this actually will stop typically with very, very few. Okay, so that's a theme I wanted to develop slightly further, and we've been looking at using this L1 idea to bound to drive a sparse canonical correlation analysis. You know, very much along the lines that Rob was talking about. You know, trying different problems and tackling them with a lasso style algorithm. We're taking, because of the applications we had in mind, and I'll show you some examples later, we actually wanted to take one view of, so correlation analysis where you have two views of the data and you're trying to find features in one and other view which the data correlates on. And we wanted to take a sort of primal sparse view on, primal sparse feature on the one view and a dual sparse feature on the other view because of the type of data that we were interested in. So we have ended up with this sort of optimization. So here, this is one view of the data, and we take a weight vector that projects it, and this is a kernel view for the other, and a dual sparse vector in the second representation, and we project them in such a way that we want the 2 norm of the difference between the projections to be minimal, and we constrain the 1 norms of these 2. Now, the solution of this, if we don't add anything to it, is going to be just 0, 0. So we need to force sort of a non-triviality, and the way we've done that is to constrain the infinity norm of this dual vector to be 1. That essentially means we're selecting one example on the one data point as sort of the key, and we're sort of mapping our thing around that. Sorry about the connected. Okay. So that's the reason for this, to force a non-trivial solution. Okay. So if we do, I just wanted to sort of briefly sketch this, because what I'm going to aim for is exactly the same thing as we've had in the case of linear programming boosting, that the L1 norm is going to drive the algorithm in terms of sort of determining which subset of variables you need to work on. So you just work on a subset of variables, get a solution, then include extra variables as you need them. So if you just do the sort of Lagrange multiplier trick and take the derivatives, set them equal to 0, and so on, you end up with some constraints like this on the dual variables, which essentially are controlling. So basically, this alpha minus will move to bound if the weight is non-zero. So alpha in this range, strictly in between 0 and 2 mu, either alpha minus or alpha plus, will mean that the weight is 0. So you can, and similarly, there's the multiplier beta, which will control the active set of indices on the dual side. So what you can do is use these to test in very much the same way as the boosting tested by that weak learner test, to see which variables you actually need to be updating. And I'm using the notation I for the indices on the weight vector side, and J for the indices on the dual side. And once you know those, actually the updates can be really done. Now, you could do this by coordinate descent. But this I'm doing as a kind of complete update. But I don't think there's a big difference there. But the key is, for me, that you've got a very restricted subset of variables you're working with, and you're just updating on those. And then you need to go back and recheck and see if you need to include new ones, and so on. And because you've got the convexity, you know that all the steps you take are going in the right direction. So this is basically the idea for that approach. And this comes straight out of the dual, as I say, optimization. So we looked at doing cross-lingual information retrieval as an example. Actually, it is an example that really needs the dual representation on the second side, but whatever, it's just to show the performance. And it's interesting because we're getting actually kernel canonical correlation analysis has been used for this for some time, and the sort of typical test is to do mate retrieval. So you have a paired corpus of documents which are translations of each other. You use part of the corpus to train to learn your feature representations, and then you test by seeing if you present one document and do a cross-lingual information retrieval, what is the rank of the translation of that document? Are you able to actually pick that one out? And this is measuring the sort of average precision error, 1 minus the average precision, as you add more projections. And the sparse version is actually doing better than the KCCA version, which is surprising perhaps, but I think it's something to do with the fact that sparsity is the right sort of constraint. I think the question asked about when do you use sparse or ridge regression. The question is, if you have an intuition that in your data the actual features that you're given are indicative in a critical way. So if you're doing, for instance, ridge regression, obviously a rotation won't change the solution if you rotate the coordinate system. But in documents, clearly words are pretty key in determining their meaning. So there's a kind of a natural, coordinate system that's given to you. And so the one norm probably is a good choice in that case. So anyway, in this case, we're getting an improvement in performance. But more importantly, we're also getting a big, saving in actual sparsity. So this is the number of words used in the actual sparse version as a function of the number of projections. And so here we're moving up to, something of the order of 450 words, whereas, if you're using the KCCA, you're going to be using all of the 49,212 words because, as you pointed out, you're always going to get a non-zero coefficient for everything. So there's a very nice kind of sparsity on the primal side and some sparsity on the dual side as well, sort of roughly a plus 50 number of documents in that vector that that around the chosen document plus the extra features that are included. So this was sort of our starting point for doing this, but we then observed actually that in a way what we've got is also could be used as a solver for lasso, because if you fix E, if I go back to the original problem here, if you just fix this and just think of it as a fixed vector, we don't need to update E. This is just a lasso problem. So the algorithm that I outlined here, basically without needing to update this, is also a lasso algorithm, and, very, very close to what Rob was saying, I think.
It actually looks a lot like Lars now, because you're actually taking steps in one variable.
Well, we're taking steps in a sort of group of variables here. Yeah, right. But ones that have been selected to be active. So it's a bit like sort of active sets in support vector machines where you sort of.
Lars does. Lars constructs an active set and puts a step in the active set.
Okay.
So
well, okay. So we've tried to do comparisons with a number of these online ones. I don't think we've compared with yours actually, but we're kind of in the runtimes we get compared to some of these are pretty good. We seem to be doing a lot better than a lot of these methods. But we definitely should try your coordinate descent. That would be a really interesting comparison to make. This was actually in a slightly smaller corpus with 2,794 words. The one that I showed above with 49,212, these methods just didn't seem to be able to handle the number of features. So we actually didn't, they were unable to solve with a large. Anyway, but we should look at this. That's a question. But just, this was actually the problem that really motivated us getting going on this, which was analyzing fMRI data. So the idea here is that you have brain scans of people doing tasks, and we're interested in the case where the task might be much more complicated than just doing something or not doing something, but there might be viewing an image or some more complicated task. And what we would like to do is have a sparse sort of weight vector on the brain scan, picking out the brain regions that are active, and a kind of more complex analysis or representation of the activity. So, maybe some kernel over images that they've been viewing. Well, this is just a very preliminary experiment, actually, where there is only a single feature on the activity side. They're just looking at pleasant or unpleasant images, so we're not actually taking into account the actual content of the image, just whether it's but this is just showing that the thing is scaling to really quite large, 211,000 voxels, 200 time points, so it's quite a small training set, and it finds 333 non-zero voxels, which to the people who know about these things appear to make sense. So you probably can't see them here, but here's just a region you can probably just spot. So it really does, drive down to an incredibly sparse set of regions. So and this is quite doable in, this is not in Fortran, I should say. But it's just MATLAB actually. But anyway, whatever. The point, this is, I think, scales very well, and I think it's very similar to what you do. So we would really need to look at it. Okay. So now, so on to my final topic that I wanted to discuss. So this is kind of coming back with the idea of sparsity as determined by a small subset of the training data. And this is actually an algorithm for sparse PCA or kernel PCA, devised by Smoller and Shulkoff. And it's actually a very neat idea. You just look for the index which maximizes this sort of Rayleigh quotient idea, and then you add that to your sort of set, and you just do it incrementally, and you can see that you will actually end up with the optimal set of indices. When you project into that space spanned by those indices, you get the best coverage of your data, the best, the maximal coverage. So it's a very it's a very efficient algorithm. And here's how you can actually compute the the projected kernel once you've selected your set of indices I. So it's not rocket science. Very sort of nice idea, very simple. But I think the thing that we realized was that actually this projection and the projection for new data just clearly depends only on the set of indices. So this is a sparse algorithm in the sense that I introduced. It's a sparse, can be reconstructed from just that set of data that you selected. And so you can just apply, crank the handle. It's slightly different from the standard because it's a regression essentially problem, not a classification problem. And so you end up with a bound like this. The expected value of your residual error on a test point can be bounded by the empirical quality of the sort of empirical residual error plus a sort of complexity term, which will depend on t, which is the number of vectors that you actually selected in your sparse set of projection vectors. This actually is a sort of plot of the bounds and a test error. Now clearly the test error will continue to go down as you add more directions. These bounds flatten off. This is an earlier bound that applies for general projection methods that aren't sparse. This is sort of indicating the quality improvement by using the sparse bound. But the nice feature also seems, our feeling is that this actually is nicely picking up on the point where essentially this goes linear, and I would suggest that indicates that this is just the residual noise. Each dimension has a noise which is just being selected. And we did some sort of artificial experiments that where we created a vector with so many significant directions and the rest were noise, and that's the point at which the noise kicks in, and indeed it does seem to be able to pick out, whereas the earlier method is a little bit underachieving in terms of the number of directions it suggests you pick. So it does seem to be, what I mean is it does seem to be able to kind of make sensible predictions about the way the data's actually being performing. So that's for the KPCA, but we're interested in this algorithm. There's a whole sort of series of algorithms that basically work in a similar way, known as matching pursuit. And what they do is they basically select a subset of the data, project into that set of data, into the space spanned by that data, and then do some analysis do some processing in that subspace. So it's a way of sort of making things much more tractable. And probably one of the better known ones is this kernel matching pursuit, which essentially just does ridge regression in the space that you create by the projection. So you project into that space and do ridge regression, and there's a nice algorithm that again can greedily choose these directions in such a way that you get, I'm not sure it's optimal, but it certainly performs well. And again, now the bound here that we get is slightly more complex because now it's not a compression scheme anymore, because you're using, you project, okay, the choice of the space is a compression scheme because you choose your data, once you know which data points you've chosen, this small subset, you know the space you're going to learn in, but you're actually using the rest of the data to, say, learn the regressor or whatever it is that you're doing. So you can't apply, the compression argument. anymore. So what you have to do is to combine it with a bound, and in this case we used a VC bound, so that you do the compression to choose the subspace and then use a sort of VC type analysis in that subspace. And you can end up with this sort of bound, which again, estimate expected loss on test points, and the way in which this is the dimension of the space enters is benign, and you actually just, well, basically add these two terms. So it's a d+1 term and a d term. This is for the actual compression part, and this is for the regression part, effectively. This is for the number of errors. So again, I think it's quite a nice scheme that you can, you're able to sort of combine this compression argument with a more standard analysis. And indeed, I think this is now quite a general technique. You can sort of crank the handle and get other approaches as well. So here's some results for the bound, actually scaled by a factor of 5, so don't be, it's not that tight, but it is at least indicating the right region at which the performance on a test set seems to have reached a good value. This is in terms of, again, the level of sparsity, so that this was the number of projection directions that were selected in before the actual regression was done. So I think this idea can be extended to a whole range of matching pursuit type algorithms. We've looked at, say, a sparse KCCA algorithm in using this technique as opposed to the one I introduced earlier. But I think there's any number of novelty detection, whatever you might consider doing. I mean, of course, the algorithmic question is, can you greedily choose these directions in such a way that you will perform well overall? So will you approach the global optimum? Clearly, computing the global optimum in terms of trying every subset is going to be too expensive. Okay, so just drawing to a conclusion, I've attempted to give an overview of a number of ways in which sparsity has been used to guide and design machine learning algorithms, and I think this compression scheme idea is very nice. It's sort of an early machine learning idea, and the analysis is appealing because it's simple, and the ideas can be quite naturally applied in this set cover machine approach, where you actually have a data dependent sort of function space that you create from your data effectively, but the bounds can still be applied. But also, as I showed at the end there, you can use this approach to analyze this matching pursuit family of algorithms, which I think are quite a useful family of approaches to analysis. L1 sparsity, we've heard a lot about, and it's a very interesting theme, and so I think it translates very naturally into bounds through this Rademacher complexity analysis. I should emphasize that this is not in any way giving you the kind of information that Yuan and Kolchinsky get out of the sparsity, where they're able to actually say something about whether the true features that are in the real thing are actually being recovered. This is not saying anything about that. It's only saying the performance will be good. But I think the point that I really wanted to emphasize in this talk was that you can use that sparsity to guide the algorithms and essentially focus down on a very small subset, typically of the variables, and by using this dual of the optimization problem, have an informed way of introducing the variables that you need to operate on, and knowing when you've actually got to a solution. And we've extended the lasso idea to this sort of double-barreled lasso, which essentially generates a feature space of projections and by an iterative algorithm again over the different projection directions. And I think this is a general method for enabling scaling to very large data sets and dimensions. So I think it's a promising approach. Okay.
very nice talk, and you showed some nice ways of using sparsity.
Thanks.
And I just want to add maybe a question about the L1 versus L2. I mean, we're saying that you use L1 when things are sparse and L2 when things aren't sparse. But also to add to that, David Donahoe, if David's still here, and co-authors have also shown that if things aren't sparse, you can't do very well at all. So in one sense, when using an L1 penalty, you're trying to do well in the only situation where you can do well in large feature spaces. So, and then the additional point which you're making, I made as well, is that sparsity can really help the computations.
Yeah.
So for all those reasons, sparsity is attractive.
Yeah, thanks.
Okay, well, now let's thank both speakers again.